Okay, well, it's my pleasure to have In Lee here, who's come from the University of Chicago, where he's a graduate student at Wayne. Before that, he was at Peking University in Beijing. He's done many things, looking at modified gravity and how that changes halo furnaces, and similar things with voids. But today he's going to tell us about some new work looking at the supersample effect in power spectrum. Hi.
Okay, thanks. Thank you all for coming. And today it's my great pleasure to share with you some of my recent research done with my advisor Wayne Hu at U Chicago and Masahiro Takada at IPMU. So I'm going to tell you about this so-called supersample effect or supersample variance. So in the first part, I'm going to tell you what it is, and after that, I'm going to tell you how does this effect changes large-scale structure observables. In this case, we choose the idealized example, which is the power spectrum, matter power spectrum. And in the last part, I'm going to tell you why do you need to care about this effect, and what do you want to do when you're dealing with large-scale structure data sets. So the first part, we know that we believe that in the beginning of the universe, there's a short period of exponential growth, exponential expansion that stretches the quantum fluctuations into tiny Gaussian seas, almost Gaussian. And after that, these serves as initial conditions that under gravitational instabilities that forms structures that we can see in surveys. So for example, here's a survey that defined by this window enclosed in yellow line. And what we see are tracers like galaxies and quasars and, for example, Lyman alpha systems that traces the underlying matter density distributions, which is usually defined as delta of x in the real space, which is the relative density distribution over some chosen reference mean density. And we'll go back to this point later, and we'll see the choice of such a reference mean density makes a difference. So given this definition, usually we go to Fourier space and decompose your matter density distribution into sums of long wavelength and short wavelength perturbations. And usually the coefficients, which we call delta of x, characterizes the amplitudes of these Fourier modes, and the matter power spectrum describes the variance of these coefficients, where it describes the level of fluctuation on different wavelengths. So this will be the observable of choice in our studies as an idealized example of this effect. So if we look at the survey with some geometry like this, we'll see that there are short and long wavelength perturbations like these yellow ones, but also there are super large perturbations whose wavelength is even beyond the size of the survey, which we'll call them supersample modes. And these modes will contribute to a non-zero mean density fluctuations. And we'll call the mean density fluctuation delta B. And this quantity delta B will receive contributions from various configurations of these supersample modes. And it is usually a Gaussian random variable. And we can calculate from theory that the variance of this Gaussian random variable using simple perturbation theory. So now I'm going to show you what is the supersample effect using very simple cartoons. Here, let's imagine there's a simple universe with only two modes. So the black one is the long mode, and the blue one is the short wavelength modes. And I'm showing you the initial conditions. Since we know that this thing is almost Gaussian, what I'm showing here is that the long and the short modes are independent of each other. They're not correlated across the space. So visualized in y-axis is their fluctuations. So the total matter density distribution would be the sum of these two in this simple universe. But we know that the gravity does not work linearly, so nonlinearity would make the long and short wavelength couples to each other. For example, in the overdense region, there will be more structures collapse compared to the whole universe, and in the underdense region, there will be less structures forms. A simple way to understand this is the picture of peak background split, where in an overdense background, there will be more peaks crossing the threshold, and in the underdense background, there will be less peaks crossing the threshold. So there will be more halos forming in this area and less halos forming in this area. And this effect, I'll refer to it later as the growth effect. But this is not the whole story. So there's another effect, which we call dilation. That comes from the fact that you can think of the overdense part and the underdense part as separate universes, while where the overdense part has a more positive curvature, while the underdense part has a less curvature. Well, it comes from the intuition that a more overdense area would behave like a closed universe, where an underdense area would behave like an open universe. And we know that a closed universe would expand more slowly as compared to a flat universe, where the open universe would expand faster. So in this case, if we think of the short wavelength modes, that corresponds to some physical features in the early universe, but later gravity would shrink the physical wavelength of this feature, but expand it in this area. So they would correspond to different sizes in different areas. And this is what we call dilation effect. So the total effect would be the sum of the two. We have growth, where in the overdense regions, short modes grows faster, and we have dilation. And in this area, it expands more slowly. And the end result is that the long modes and the short modes are coupled. They're no longer independent. They're correlated. And by definition, we call that this is the non-Gaussianity produced by gravitational structure formation. Right? So, yeah, this is... Well, and the total effect is what we call the the supersample effect. And
Gaussianity refers to the distribution function of the modes. I think what you're referring to as non-Gaussianity, you actually mean statistical isotropy, that modes at different scales are correlated.
Gaussianity in Fourier space means different modes. Well, if you have an infinite volume, then it means different modes are not correlated. You can describe the whole distribution just by a two-point function, right? By the power spectrum. Where in this case, the power spectrum is not enough for describing your density distribution.
Yeah, we can talk about it, but this is called statistical isotropy. We'll talk about it.
Statistical isotropy.
It's just a name.
Okay, if you say by definition, this is called, but I think Gaussianity means that you only need the two-point function or the two moment to describe your random fields. But here, non-Gaussianity, well, it means that the short modes and the long modes are coupled. They have different wavelength. In Gaussian field, they are not coupled, but now they are, right?
Yeah, which means that in the covariance matrix, you have off-diagonal elements.
Yes.
And they can be two-point functions still, but they are not.
Well, yeah, you can be produced by the window function. That's true. But here, at the beginning, I assume an infinite volume. So the window function disappeared. In this case, the only.
I think what you're talking about is that if you take a statistics textbook, Gaussian means that there exists a linear transformation in which the covariance matrix is diagonal and given by a Gaussian. You're just saying that this coordinate system.
I'm referring.
Has a coordinate the way that it is true, which you haven't said it before.
Yeah.
Lensing is the equation of stationarity.
Okay.
That is, you could use the wrong coordinates. But there exists clearly a transformation where it is Gaussian. So it's Gaussian, but not stationary.
Okay.
And that's the question. And in this case, I'm not actually sure whether it is actually Gaussian, but it's certainly not stationary.
Okay, stationary. Yeah, it's these coupling makes it not stationary. Well, this. Right. So, yeah. So if we choose our survey region or observed region as depicted here as the box, but in this case, we're either choosing the left or the right, but we don't know which one we're choosing. Or in other words, we don't know the amplitude of the long wavelength perturbation. But as we've seen, that the long wavelength does affect the short dynamics. So how does this work out? We don't know. There's some effect that changes your observables in the volume, but you don't know how large it is because you don't know the amplitude of the long modes. So we can take this into account by modeling this as an additional error. But on the other hand, if we know exactly how does this long modes changes this short modes, we can, given the data set, we can try to measure or constrain the amplitude of the long modes indirectly from your observation of the short modes. And this alternative view is to treat the amplitude of the long modes as a signal. So I'll talk about these two different routes in my third part. But before going into the second part, I'm going to distinguish between two classes of observables. Well, in this talk, I'm only focusing on the matter power spectrum, which underlies large classes of large-scale structure observables, such as galaxy clustering or weak lensing, right? But there are some subtle differences. For example, in galaxy clustering, we're going to measure the mean density fluctuation by counting the total number of galaxies in your survey volume. And that measured reference mean density, we'll call it rho bar local. But for weak lensing, we know that it is affected by the relative mean density fluctuation with respect to some global mean density. And in that case, the reference mean density is called rho bar global. And they're related by this simple relation. And if we plug this into the definition of power spectrum, we see that the two classes of observables are related by this simple relations that differ by this multiplicative factor. And we'll go back to this later and see the difference it makes. So in the second part, I'm going to talk about how does this effect changes the observables, in this case, matter power spectrum. So I'm going to tell you that I'm going to prove this in my third part, but first let me tell you that the supersample effect can be produced by many different large-scale modes, but eventually you can simplify this by describing this effect by the response of the observable to the mean density fluctuation, which is what we define as delta B, right? So all these different possible configurations all contribute to this delta B, but we don't have to know how our observables changes with respect to all these different possibilities. We just need to know how do they change at the presence of this single mode. And this single mode the change can be written as this, which is the fractional response of your observable with respect to delta B.
So this is the ensemble average of such volumes?
Ensemble average. This is per realization. This is the mean density fluctuation in the volume. Yeah. But you can write it as a sum of all different, long modes, convoluted with your window function, so such that all long modes would contribute to this mode. So, if seeing that the two different classes of observables differ in their definition, if you take ensemble averages on the right-hand side versus the left-hand side, we'd see no difference because this thing has an average 0. But per realization, if we want to know how does the P local versus the P global respond to a change in delta B, they would have different responses. You can see that by simply taking a derivative and the fractional change of the left-hand side and the P local, the fractional change in the P local differ by just a constant factor of 2. Right. So for the global type observables such as weak lensing, they would have a much larger response to a change in delta B. While versus, galaxy clustering, they would have a smaller response.
So this Q global is like the power spectrum on.
Not the whole universe, but you would see the volume enclosed the lensing region.
Okay, but delta B is like the mean in that volume, or? So when you talk about this supersample mode, is that mode larger than the volume of this Q global, or?
Delta B is in this case, it is what you measure as the local mean density versus.
Shift in the mean value of this supersample mode, right? Like it's like a homogeneous shift. The shift that looks like a homogeneous shift within that sample volume, right?
We're modeling it. We're modeling delta B as a overall. What do you? What do you?
Oh, yeah,
yeah.
I think,
Yeah.
I agree with you.
Yeah.
And well, I'm just trying. So local is a smaller volume of global, or?
In this local case, is that your reference mean density is what you measured, and in this global case, you don't care about, because it's not, for lensing, it's not sensitive to the local reference mean density.
Okay, so P global doesn't depend on delta B.
Well, I'm just saying, okay, let's go to the first. Wait, I'm just saying that here's the reference mean density appears in your density fluctuation. In one case, you measured it and you plug it in here. In the other case, it didn't show up in your equations, so it's. In the lensing, in lensing, there's no input here. For lensing, it's just sensitive to the relative mean density.
So you're just saying in the case of like a galaxy survey where you're counting numbers, like you count. You're just saying that you count the local number of galaxies, and then you also calculate the average number of galaxies and divide it.
Yeah. That's.
You don't have to do that for a weak lensing survey.
Yeah. That's what I mean. Yeah. Yeah. So, how do we characterize this function? Yeah. So we run n-body simulations, which is pretty much the only effective way to deal with nonlinear structure formation. For example, if we want to know if this box is comparable to our survey volume, we want to know the super sample effect, super sample effect produced by modes larger than this volume. It would run a small box simulation like this big, but the limitation of n-body simulation is that the periodic boundary conditions would eliminate all modes that are larger than the box sizes. So to achieve this, to incorporate a mode that are larger than the box, you need a large box simulations. And then you look at the subvolume of the large box simulations, which contains large long wavelength perturbations. But this approach is expensive because since you want to know the covariance, you want to know your observables in this volume, but you have to run a large box simulations. And it's much effort in coding and computations. Fortunately, there's a way to circumvent this limitation. There's clever tricks to incorporate a mean density in your box effectively. So to start with, we want to know what the structures, what the observables look like given a set of cosmological parameters and some non-zero chosen mean density shift. We can absorb this non-zero shift in mean density into a redefinition of your cosmological parameters. And you can derive it quite simply, both using Newtonian mechanics, Newtonian physics, or general relativistics derivations, that they should satisfy such a simple. So in this line, this is a relative shift in your cosmological parameters, and they obey this simple relation. And note here that if you start, you have a question?
Sorry, I just had a question. I think it's connected to Takeshi's question, but I think when you're talking about n-body, what you do in n-body, in principle, if I didn't tell you the power spectrum ahead of time, this argument would say, well, I could have an arbitrarily long wavelength mode, so it had this, the only simulation that captures all the long wavelength modes this way would be an infinite size box.
Yes.
But of course, that's not what people actually do, because all you really care about is getting over the hump, right? So that you know the power spectrum goes to zero on sufficiently large scales, so you don't really care about those. So isn't that what you mean by the separation between local and global? The local ones are the ones where you're smaller than you have a lot of power outside of your box versus you have a sufficiently large. You're set. You only just
I think the difference between local and global are just, as Richard said, it's.
Well, in the weak one thing survey, if there was a mode that was 10 times the size of the observable universe, it would locally change our cosmology.
Yeah.
And it would locally change that, and you never.
I'm not referring to super horizon stuff. Yeah.
But the reason you don't care, one reason you don't care about that, the super horizon, is because there's no power out there anyway. It doesn't change. You don't have to take that into account. Whereas if you're local, you can do bigger experiments and you see that effect. But I think if you were sensitive to the modes outside the horizon, then you actually, when you in principle have to take that into account when describing global parameters versus local parameters. I mean, it's always local. Every measurement is local.
Yeah. In some sense, yeah.
Local and global, I would have thought is when you're over the peak, so that there's no power.
Yeah, maybe the global is kind of misleading, but they just mean that in one case, the reference mean density is what I can measure from the survey. Yeah.
But but coming back to the n-body, is that what you actually would do in n-body? In n-body, you would just say, make a big enough box so that I know there's no power outside the box. Is that for the long term?
So if you increase the size of your box, the power outside the box is getting smaller and smaller, but you're getting more and more information. So let's take survey as an example. If you observe more volume, there's less and less power outside the volume, but also you get more and more information, such that your error bars on your cosmological parameters are getting smaller and smaller. So what you want to compare is the rate of the change of the error bars on your parameters to the amplitudes of the long modes, and they change relative.
That's sensitive to the shape of the power spectrum.
Mhm.
So the answer
Yeah.
for where you get to go is the fact that there's, I mean, if I was talking about small, if I took a really tiny box,
Mhm.
it's such that if the power is growing outside, it doesn't make a huge difference to the size of the box. Whereas, so that deciding where the box is big enough is sensitive to what the situation is. Is that fair, or is that a correct statement?
Can you repeat the last sentence?
I thought you just repeat what I think was said. Sorry, I just thinking because I think I heard something different from what you heard. Let me try to rephrase what I think you said, and you tell me whether I got the wrong one as well. Which is, I think what you said is the difference between P global and P local when you measure the power spectrum of a sub. I've got a gigaparsec simulation and a 100 megaparsec sub volume. To define the power spectrum, I take density in the small volume. If I divide it by the density of the whole box, I call that P global. If I divide it by the density of the 100 megaparsec thing, then I call that P local. That's the only difference.
Yeah, that's what I meant. Yeah.
And you're always only sensitive to the local variations, right? Like in our visible universe, we don't know that there's not a, I guess I'm more actually just trying to understand what the depth. So if you pick a different universe where all the long wavelength modes were dominated by the ones that were outside the volume, like most of the power of the long wavelength modes was coming from modes larger than the observable universe, then it would tell you that to pick up this effect, you have to observe, you have to simulate. So you have to simulate boxes bigger than the universe. Whereas if all the power is dominant, the long wavelength, if the power goes to zero very quickly, then who cares? You pick a small box. So decide what you pick is the size of this box compared to the size of. You wouldn't care about this effect if it wasn't for the fact that there's actually a significant amount of power on large scales compared to a given simulation.
No, I think it's just when I tell JD to take a sub box and measure the power spectrum, he'll ask me, do you want me to divide by the volume of the sub? Do you want me to divide by the mean density of the sub box, or do you want me to divide by the mean density of the whole box? He'll ask me that question, which is the same in his language, saying, do you want me to measure P global or P local of that sub patch? And I have to give him an answer. And after giving him the answer, I'll often tell him, oh, by the way, these are related by PB, delta PB over delta B minus 1. That's all good. That's what I think you would tell it. It's independent of volume, independent of anything. That's the fact that if you have a subsample, you have two choices of what you mean by definition of power. I think that's all he's saying. It's just saying.
If you're taking a subset, okay, I agree with that.
Then it sounds like the only difference between P global and P local is basically this renormalization part, right?
Yeah.
Then how is P global? So you have this expression where you were varying P global in terms of delta B, but isn't that zero?
This one, P global.
Because over all volume.
This is not the power spectrum of the all volume. This is the power spectrum in the subvolume.
But according to what I just heard, the only dependence comes in by how the well, I just thought that
This is there.
Through the normalization parameter.
The only difference in P, it comes from the reference mean density, a change in the reference mean density.
The big scales, I mean, the mean value on the big scale doesn't care about the delta B, right? Because the big scale, sorry, the scale where the average delta B vanishes, right?
So your delta B is always defined with respect to, say, the cosmology in your horizon, I think. So it's not zero delta B. It's not zero. It's you assume that you know the true mean density is, and you calculate delta B with respect to that. Does that make sense?
Maybe I'll listen to you and
Yeah.
maybe I'll
Yeah.
understand it.
So these are simple prescriptions that once you do, you can simulate effectively a non-zero mean density box. And if you look at here, it means that if you start with a flat universe, then what you simulated is a curved one with non-zero curvature. And this effective universe scale differently when you compare that with your initial universe. And you've also fixed the high redshift physics by keeping AS and NS the same. So if you can do this trick, then you can calculate this simply by doing a finite difference. Well, you simulate a universe with positive mean density and negative mean density fluctuation and take the difference. And you can calibrate this derivative. So in principle, you just need to run 2 simulations. And I'm going to show you the 2 techniques that we use to construct this derivative. The first technique for the initial conditions in the high redshift limit, we introduce 2 simulations. In the one case, it has positive delta B and negative delta B. And we start them with the same initial random Cs to remove most of the stochasticity. And at the targeted end redshift, we stop the simulation. And at that redshift, they happen to have the same box sizes because of dilation. And now we can take the difference to calibrate the derivative. And this calibration would contain both growth and dilation effect.
So you put your boxes near the maximum minimum of your long wavelength.
This is just for visualization.
There's no curvature, it's just flat. Well, this leads to my question. You're dealing with a mode which is somewhat larger than the box, so you obviously cannot capture its dynamics.
Yeah,
Don't you have to also include a gradient here?
Yeah, sorry. This is just for visualization, since this trick.
Just for visualization.
This trick.
My question was, don't you include
Oh, you mean if I really want to introduce these inhomogeneous long wavelength perturbations, then I would just run a large box. Instead of doing this trick, I would just run a large box.
What he's saying is this accurate?
Is this accurate? Okay.
Well, it's not too much of a generalization to go add not just constant offset, but a gradient, right?
So if you subtract a constant offset from it, it's
Why?
So the way it works is that we change one parameter to limit over density.
I understand, but you can't do that with a gradient.
so you want to say something like this?
I know. That's why I'm asking the question.
A gradient. I think for the thing that we are looking at, the gradient doesn't make much difference, but it certainly changes your observable in some way. Yeah, but if you look at the monopole power spectrum, I don't think it will make a bigger difference than this effect. So this is the first technique, which captures both growth and dilation. The second one, we start our simulation, or in the high redshift limit, we start the simulation with 2 boxes of the same size, but with different delta B and the same Cs. And later, because of dilation, we see that the red segments in the box dilate at the same rate, such that at the initial conditions, if the red segment here and here correspond to the same feature in your of some primordial power spectrum, and this feature would dilate to different wavelengths here versus here, but the box is also expanding at the same rate. So when you take the finite differences, you're differencing this with that, and so by doing this, we're factoring out the dilation, but only calibrating the growth effect. So I'm telling you that by using 2 techniques, we can calibrate the total, and we can calibrate the growth. That means we can take the difference to know the dilation. But On the other hand, we can also just derive analytically what the dilation looks like. It just looks like a derivative of your power spectrum. It's very simple. So that said, we know how to calibrate from simulations, growth plus dilation. We know how to calculate the dilation by taking derivatives of the power spectrum. We can also calculate the growth only. And I'm showing all of them here, which gives you a cross-check of our calibrations. So in blue is the second techniques, which tells us the growth only. And in black is the first techniques, which gives us total. And the green is the derivative of the power spectrum, which gives us only the dilation. If we add the dilation to growth, we get growth plus dilation, and it agrees with our total perfectly here, which means that we have an accurate physical separation of the two effects, and they sum up to our total supersample effect. And we want to compare our simulation with previous analytic and semi-analytic predictions of this effect. So in the linear or quasi-linear regime, people use second-order perturbation theory to calculate how does your power spectrum change at the presence of delta B, which is just a constant factor here as your fractional response. So in the nonlinear regime, this second-order perturbation is no longer accurate, but we can do some semi-analytic calculation using halo models. So this halo sample variance is just telling you that in the positive delta B, there will be more halos. Your halo number, your halo abundance would increase, and thus increase the nonlinear power. And we also found that in the second-order perturbation theory, in the literature, there's one effect missing. So we included in our studies, which is what we already know, the dilation effect. If you do the second-order perturbation carefully, you would see that this terms pops out as if you integrate your F2 kernel in your perturbation theory carefully, there's a pole there. If you miss it, you don't get this term. If you be careful, you get this new effect. And this is the same physical effect that shift your BAO peaks in the subvolumes. If you have a large volume of galaxy survey, in each subvolumes, your BAO peak would shift to smaller or larger scales depending on the local delta B. But yeah, this is the same effect as that. Sorry, how much time do I have?
We have follow-up questions, so about 20 minutes.
20 minutes. Okay, so we can combine all these previous ingredients, like beat coupling, halo sample variance, and linear dilation effect. We can combine all of them using halo model, and sum all three terms up. We get this total. And what we want to do is we want to compare this semi-analytic prediction with our simulations. And this is what the result looks like. At two different redshifts, redshift 1, we just scale it by a factor of half for clarity. And solid line gives you simulation. Solid line gives you halo model prediction, and dot are simulation results. And they agree to 6%, which means that the halo model are relatively accurate to 6% across this range of wave number. So now we know how does the power spectrum, how does the supersample mode affect your observables? But how large is this effect? Why should you care about it? if it is important, how do you take that into account? So as I've shown you that we can take two perspectives. We can see this as an additional source of error. We can see it as a new signal. First, let me focus on the first perspective. So to characterize errors in your measurement, we usually use covariance matrix, right? So a covariance matrix in this case is defined in this way. We know that the diagonal term tells us the variance of your measurement on different modes, and the off-diagonal terms tells you the correlation between measurements of different modes. And in this case, we can divide our total covariance into three terms. Well, actually, first in two. The first is the Gaussian piece, which we denote by CG. And CG, in the ideal case, if you don't count in the mode coupling produced by window, it's almost diagonal here. And the nonlinear pieces are the rest two terms. First, the second term. First, let's look at the CT0 term, which is the non-Gaussian term produced by direct nonlinear mode and nonlinear mode coupling. But what we introduce here is the third term, which we call the supersample covariance term, SSC. So this is an additional term that is not usually included in the current data analysis. It's also a non-Gaussian piece, but it's produced by the nonlinear mode coupling induced by at the presence of a long wavelength perturbation. So all modes are scale. Let's see. So the Gaussian piece would usually dominate in the linear regime, and the non-Gaussian piece would dominate in the nonlinear regime. So this is how we derive it, analytically, by using the trispectrum consistency relation proposed by Masahiro and Wayne last year. So you can make an analogy to the multi-Sina bispectrum consistency relation. In that case, it's a squeezed bispectrum. But in this case, it's a squeezed trispectrum. So it is a squeezed quadrilateral configuration. If you plug this trispectrum into your covariance calculations, you get a nice separation between the second piece and the third piece that we saw, which is the CT0 and the supersample covariance. So let me focus on the supersample covariance term here closely. So this formula is telling you that the magnitude of this covariance is proportional to the variance of your long wavelength perturbation, and also proportional to the response of your observable to this long wavelength perturbation. And as we've seen, as we've discussed, I'm distinguishing between two types of observables, and they differ by a constant factor of 2. So I want to calibrate this. So given the covariance decomposition, we want to calibrate each piece using simulations again. So this is our sets of simulations. I've already seen that for a box sizes, in this case 500 megaparsec, it doesn't contain long wavelength perturbation larger than this size. So if we run this many simulations and we calibrate the covariance matrix using them, we don't have, their covariance doesn't contain this piece. Whereas if we run 7 huge box simulations, in this case 4 gigaparsec and divide each into 500 parts, resulting in this many total sub-boxes, like this big. And we can measure power spectrum in each sub-boxes and calibrate the covariance of the total 3,000 sub-boxes. And because there are modes that span, that has wavelength larger than the sub-boxes, you also receive contributions, the super sample covariance contributions. So you can take the difference to get the super sample covariance only. So to be specific, this is how we check our SSC model. First, this is our model. We want to check if this is correct. We can calibrate the response using separate universe simulations. And then we have small box simulations, which receive contributions from the first two terms only. And we have large volume simulations, which receives contributions from all the right-hand side. And so that said, we know exactly each pieces in these equations. So what we should do is to check the equality of this equation. And so this is the result. In blue, blue tells you the covariance. Actually, I'm only showing the diagonal. So this is the variance of the small boxes simulations. Visualized on y-axis is the non-Gaussian variance to Gaussian variance ratio. And in black is the sub-box results. So to be specific, here, blue tells you the ratio between the second term to the first term, the CT0 non-Gaussian term to the Gaussian term. And in red, I'm adding the third term, which is the supersample covariance term, to this result, which is, so the red is the total non-Gaussian covariance to the Gaussian covariance. And by constructing this, so now we see that the black agrees with the red across the whole range almost perfectly here to percent level. We know that this effectively checks the equality of our previous equations, which is this one. So this is for global type power spectrum. For local type power spectrum, again, we do the same thing and to check the equality, but here we see that the difference between black and blue is much smaller. Across the whole range is about 50%, meaning that this term is about 50% of that one. While in this global case, this is a much larger difference, meaning that the supersample covariance is much more, is actually dominating the non-Gaussian error budget. But still, in the local power spectrum case, this supersample covariance is still a significant piece in your error budget. Let me skip this one. So here, we've seen that this effect is important because it introduces a significant piece in your covariance matrix. But another view of this effect is that we can take delta B as a new parameter. We can write down a simple model like this, which says that the power spectrum, at the presence of a delta B, you can express it as the power spectrum at the absence of delta B plus some constant shift. So this is the simplest model that you can write down. It's an additive model which doesn't change the statistical property of your observable, which means that you don't even have to modify your covariance matrix in your data analysis pipeline. So writing down this model, how well does it work? We can check since we have so many subboxes, we can check this model on each of them and estimate the delta B of each subboxes. Right? So shown here is since it's simulation, we know exactly how large the delta B is. And given the estimator, we can estimate from the simulation net estimated delta B. And we bin them in a quarter of the RMS of in delta B. So shown here is that they line up very well on this unbiased diagonal line, meaning that if I know that this delta B is here, then my estimated delta B is also in this region. And equivalently, I can show you the distribution of the estimated residual in unit of the RMS of delta B. In this case, since we know the global type power spectrum has a much larger response, that means your observables change more violently, and that gives you a better estimate of delta B. While in the local case, a smaller response would give you a more spread out estimation of delta B. Since we can write down the estimator, we can also calculate, what's the estimated variance of this estimator. And I'm also showing them here as a Gaussian, which matches our probability distribution very well to 7%. And this means that our model, the simplest supersample model, captures this effect, most of this effect, up to 90%. Finally, having introduced you to the two view of this same effect, we can try to see how should you take this effect in your data analysis. Let me take the second view. That is, we take it as a new parameter, and we look at the cosmological parameters, and we think that we should do a joint estimation of this new parameter together with other parameters. So this is a set of lambda CDM, vanilla lambda CDM parameters, and we eliminate the last two because we know that the CMB constrain them very well, and also they would change your BAO peaks, the shape of your BAO peaks, so that we're only looking at the first three. So they are more degenerate with our new parameter. And so our parameter space is 4-dimensional, which include this new parameter and other 3 parameters. And similarly, we can calibrate our observable, the response of our targeted observable with respect to all these new parameters using the same techniques from simulations. And what do they look like? So the red is how does your power spectrum changes at if you change your AS, and the blue is how does your power spectrum changes if you change H, but keeping omega matter H squared fixed. And the red is easy because when you change the tilt, your power spectrum increases on the small scales and decreases on the large scales, right? So you would think that if one of these parameters changes your observable exactly in the same way as a change of delta B, you would have a complete degeneracy. So let me remind you, what does the response to delta B looks like, which is using T as the fractional response of P to delta B. Here, global and local shows you the constant shift of 2. So this is what you have seen in part 1. So they look quite different, right? So your power spectrum will respond quite differently to each individual parameters compared when you compare this to this. But however, since this is a 4-dimensional parameter space, you can do some linear combinations of these response functions. And if they mimic any of these, you will have a complete degeneracy. So this is exactly what we found in the local case. We almost have exact degeneracies as is depicted in blue here. So this is a Fisher analysis before, given the covariance matrix and models, we can look at the covariance between parameters. And this tells us that in the local power spectrum case, there's almost an exact degeneracies between our new parameter and some linear combinations of cosmological parameters. Well, this is absent in the global case. And if you look at the blue line here, which is almost circular.
Just to make sure, on the left you're saying that if you just have local observations, like delta B can be shifted into the renormalization of other cosmological parameters.
Yeah.
Is that basically what?
Yeah, that's before. Yeah, that's when you just look at the joint analysis, but you have prior informations of how large this delta B can be, because we know it's a Gaussian random variable, and we know that it should be some Gaussian random variable with some variance, right? So it has a large degeneracies, but we know that, for example, delta B is here. We know that delta B should be somewhere in this region. So that gives you additional information on. After that, after you introduce this prior informations, that you can eliminate most of these degeneracies.
If you have a prior, you don't even need anything, like you already know.
Well, yeah, if you know exactly what delta B is, that's another story. But here we.
Your width, your uncertainty shrank would have been the same width if you had done nothing at all. Just told me I know if I have sigma B, I could have told you what the distribution of delta B is. It's just a Gaussian of e to the minus delta B squared over sigma B squared, without spending a lot of time doing simulations. I could have told you that.
Yeah. This prior information is, I don't need to run simulations to know.
Yeah.
Yes.
Yeah, and since the other one makes almost no effect on it, I could have just saved what I've got a book.
Yeah, I'm going to show you the exact number. How does this thing change? Sorry. So this just gives you an qualitative feeling. How does the degeneracy structure look like? But here it's quantitatively how much does error degrade. So to know, let me explain. So here I'm define degradation as the error if you don't know delta B, divided by the error if you know that exactly. So this is actually how much you are over-optimistic about your constraint on cosmological parameters. So if it is 1, then you're not over-optimistic at all. If it is 5, then you overestimate your constraint, overestimate your error bars by a factor of 5. So here I'm choosing a idealized cube geometry of volume 10 gigaparsec cube, and also idealized window being 1 inside the cube and 0 outside, and this is the forecast. Each number is showing this over-optimistic value. So I'm just choosing an example for log AS. I'm not showing anything else. So before you adding the prior, you're over-optimistic by a factor of 4. That's bad. For global and for local and for global, it's over-optimistic by 50%. But since you know that delta B has some constraint, it's a Gaussian variable, and you can calculate its variance, And after you put in the prior, you're over-optimist by 10% and 15% here. Right? So I'm not showing you any other parameters, but actually I can, in this whole parameter space, I can find the certain directions that, which this is maximized, right? So you actually, in some combination of the parameters, you're most over-optimistic. In that combinations, this ratio is 5 here for local, but after you put in the prior, it's similar, 10%. But for global, it's quite different. Before you put in the prior, you're over-optimistic by a factor of 3. But even after you put in the prior, you're constrained on the whole cosmological parameter space. It still has a large factor here. It's a factor of 2. So that's that. It means for lensing, this is really a big effect. But still, for galaxy clustering, this is also non-negligible. And the realistic number, if we took, because here I'm using an idealized geometry and idealized window, the real number should be somewhere in between these two. So it's not totally this number or that. Yeah, so this is something work in progress. What I've told you, everything before is the 3D case. The 3D monopole power spectrum changes at the presence of a 3D over mean density fluctuations. But in realistically, we look at observables, which we integrate over along the line of sight over different redshift slices. So what really should be considered is the transverse power spectrum at the presence of a transverse mean density fluctuation. And here I'm showing you the difference between the responses, which actually here it's not clear, but here the prediction, the calibration agrees with second order perturbation theories very well. And here is telling us that on the smallest scales, in the transverse direction versus in the 3D angular average, there's not much difference in the two responses. So in the summary, the takeaway message is that the supersample effect can be broken down into growth plus dilation, where the latter has been previously ignored in the literatures. And also, this effect contributes to a dominant or significant non-Gaussian errors in your error budget. So it should be considered when you are analyzing survey data. And it can be conveniently treated as a new parameters, which requires minimal modifications of your data analysis pipelines. And as a result of this effect, your constraints on cosmological parameters are degraded. And for future projects, we want to do some more halo calibrations to build a bridge to real data analysis. For example, we're trying to apply our analysis to BOS data. And also, we need to model realistically in real surveys the redshift space distortion effect. And to also make this available to all future surveys, we want to build emulators of various possible large-scale structure observables with respect to supersample modes. So yeah, so thank you.
We have quite a few questions during the talk, but if anyone has a quick question, something they'd like to ask? Before we wrap up?
Well, realistically, how well could you constrain delta B with upcoming surveys?
Yeah, that's an interesting question. Yeah. So my impression is that it doesn't tell you too much about delta B. Certainly, if delta B is simply within, if the amplitude of delta B is as small as what linear perturbation theories tells you, then it's not a very strong constraint. But if it is very large, it is something crazy, then you can measure it actually. Yeah. So one of my collaborator, Masahiro Tagada, is actually very interested in measuring the difference in delta B between the south and the north patch of Boss data. So he's hoping that this can possibly explain the CMB, anomaly. Yeah, but if delta B, is small as predicted by sigma B, which you calculate from linear theory, then and I don't think it's a strong constraint. If you,
Great. I think we'll hopefully be taking out to dinner tonight. So if anybody is like to come on, please let me know. We'll try and confirm that later. I think upstairs there will be cookies for those who are not allowed to be strongly positive. And I guess you might like to go out for lunch or something. Who wants to go out for lunch?
yeah, I can get a quick lunch. Yeah.
Yeah. Anyway,